In this module, we'll check out concepts that help us interact with the running operating system, and we'll look at how we can get the most out of the tools available. We'll kick this off by talking about how to read user data interactively. Then, we'll explore the standard input and output data streams provided by the operating system and see how we can interact with them, both from Python programs and from the system programs. In a lot of our examples, we'll interact with the operating system through the command line, so we'll start familiarizing ourselves a bit more with the Linux shell. We'll also talk about how we can execute system commands from Python. This allows our scripts to harness the power of the rest of the operating system. So it's important that we know how to manipulate the output of these commands and handle any generated errors. We'll wrap up by diving into one important source of information for IT specialists: log files. We already got a peek at a few log files in some of our earlier videos. Now, we'll look at how we can make sense of the information these log files provide by using the tools that we've learned throughout the course. So there's a bunch of interesting things ahead of us. Are you excited? 'Cause I'm excited. So what are we waiting for? Let's dive in. We've talked before about reading and writing files. Using files to store information and then processing that data with a script is a great way to build automation. But sometimes we need to interact with the user and ask them for certain pieces of information that just can't be stored in a file. To do this, Python provides a function called input. This function allows us to prompt the user for a certain value that we can then use in our scripts. Let's see what that looks like. Here we have a script called hello.py. It's a very simple script. It asks the user for their name and then prints a greeting that uses that name. Let's execute this script to see it in action. Hi computer. The input function always returns a string. If we want the data that we're reading to be a different data type, like a number or a date, then we need to convert the string to a format that we want. Let's look at a different example. This script does a bunch of things, so let's go over it piece by piece. First, we define a function that converts into seconds the number of hours, minutes, and seconds. The actual program starts by printing a welcome message and then entering a while loop. See how we first initialize the const variable that we'll use to check whether the user wants to continue or not? In the body of the while loop, we ask the user to provide the number of hours, minutes, and seconds for the conversion. As our 2seconds function requires integers, we're converting the value returned by the input function using the int function. With those three values, we then call the function and print the result. After that, we ask the user whether they want to do another conversion or not. Let's try the script out and see what happens. Great. Our code seems to be working properly. We entered 3 numbers and it did the right conversion. It's now asking us whether we want to continue or not. I think we have the time to answer, don't you? Let's say yes. This time, we said that we didn't want to continue, so the program finished and exited. And with that, we've seen how we can interactively ask the user for input. We're only a few minutes and seconds into this module, and you've already learned a new concept. Just imagine how much more you'll learn by the end of this module. Interactively asking the user for input might not always be the best approach for a problem we're trying to solve, but it's a great tool that you just added to your IT toolbox. We've now seen a couple of ways of getting information into and out of our scripts. We know how to read and write to files and accept input from the keyboard and print it to the screen too. But what exactly is going on behind the scenes when we do this? How does a Python program connect to both the screen and the keyboard? Well, it uses I/O streams. I/O streams are the basic mechanism for performing input and output operations in your programs. You can think of these streams as pathways between your programs and their input sources, like a keyboard, or output, like the screen. I/O streams aren't just available for Python programs. When we run a system command on our terminal, I/O streams are also being used to connect that command to the terminal input and output. This way, we can see the results of the command or enter data interactively if that's how the program works. We call these streams because the data keeps flowing. A program can read input and generate output as long as it needs to achieve its goal. Okay, but what do these streams mean in practice? Most operating systems supply 3 different I/O streams by default, each with a different purpose. The standard input stream, commonly referred to as std_in, is a channel between a program and a source of input, usually in the form of text data from the keyboard. When we use the input function to accept user input in a Python script, we're using the std_in stream. The standard output stream, or std_out, is a pathway between a program and a target of output, like a display. std_out generally takes the form of text displayed in a terminal, as is at play when we use the print function to write information to the screen. The last type of pre-made I/O stream is called standard error, or std_err. Standard error displays output like standard out, but is used specifically as a channel to show error messages and diagnostics from the program. It's usually printed to the screen. If you've ever run some Python code and received an error, then that error message was probably printed using standard error stream. Let's see this consolidated in an example. Our script here has 3 lines. Each line is interacting with a different stream. In the first one, we read from standard input. In the second one, we write to standard output. In the last one, we generate an error by concatenating a string to an integer. This error will be printed to standard error. Let's try it out. So, we first read some data through standard input and then printed it to standard output. Python then printed a type error because we tried to do something weird. As we called out earlier, these I/O streams aren't restricted to just Python programs. For example, we've been using the cat system command to display the contents of a file. When we do that, those contents are printed to the terminal using standard output, like this. And when one of these commands generates an error, that error is displayed to standard error. For example, if we use an unsupported flag with the ls system command, which normally shows the content of directories, we get this error. I know, it looks like standard output and standard error are the same here. That's because they both get displayed to the screen, but they're actually pretty different. We'll look into exactly how they're different later in the course. I'll keep you in suspense for now. We'll keep coming across these streams in our Python programs, so you'll start to become more familiar with them. And later on in the course, we'll even learn how we can redirect them to other files and other processes. The key takeaway for you to remember at this point is that I/O streams are ways for programs to give and receive information. In the next couple of videos, we'll take a look at other ways that we can provide information to our programs, environment variables, and command line arguments. When we open a terminal application on a Linux computer, whether it's local or a remote machine, the application that reads and executes our commands is called a shell. A shell is a command line interface used to interact with your operating system. The most commonly used shell on Linux is called bash. Other popular shells are ZSH and fish. While they operate in similar ways, for this and upcoming videos, when we talk about the Linux shell, we mean bash. Our Python programs get executed inside a shell command line environment. The variables set in that environment, which are called, you guessed it, environment variables, are another source of information that we can use in our scripts. Understanding and being able to change environment variables can be really useful to quickly alter a program's behavior. Usually, we can do this by just making some minor changes in the environment the programs are running in. From a command line prompt, we can check these variables using the env or env command. Let's take a look. Whoa, that's a lot of different variables. But what are they for? It all depends on the variable itself. Some are more important than others. For example, the path variable is a very important one. Let's print out the contents of just that one using the echo command. As a refresher, echo is a command that we use to print text in the Linux shell. And when we want to access the value of a variable in this shell, we need to prefix the name of the variable with the $sign. Here, we've printed the contents of the path variable. The shell uses this environment variable to figure out where to look for executable files when we call them without specifying a directory. All those directories listed there are where the shell will look for programs. For example, when we call the Python3 program, the shell checks each of the directories listed in the path variable in order. And when it finds a program called Python3, it executes it. So, as we said, we can read the contents of these variables from Python. Let's use a Python script to check that out. So, to access the environment variables, we use the environ dictionary provided by the OS module. In this case, we're using a dictionary method that we haven't used before. The get method is a bit similar to how we've been accessing dictionary values up until now. The difference is what happens when the value isn't present. When we retrieve a value from a dictionary using the key, as in os.environ fruit, and the key isn't present, we get an error. If we use the get method instead, we can specify what value should be returned if the key isn't present. In other words, the get method allows us to specify a default value when the key that we're looking for isn't in the dictionary. So, what we're asking Python to do is try to retrieve the value associated with the key, but if the key is not defined, return an empty string instead. We're doing this for 3 different variables: home, shell, and fruit. Let's run the script and see what happens. We got the values for home and shell, but not for fruit. Well, that's because that variable isn't defined in the current environment. To define it in a way that our script will be able to see it, we need to run this in our command line. So, we define the variable by just setting a value using the equal sign and leaving no spaces in between. Along with this, the export keyword tells the shell that we want the value we set to be seen by any commands that we call. Now, let's call our script again. Cool. This time, we got the value that we wanted. So, you now know how to get the value of any environment variables from your Python scripts. Up to now, we've seen how different programs can read from and write to standard I/O streams, and how the shell environment can influence the execution of a program. Yet another common way of providing information to our programs is through command line arguments. These are parameters that are passed to a program when it started. It's a super common practice to make our scripts receive certain values by command line arguments. It allows the code of the script to be generic while also letting us run it automatically without requiring any interactive user input. This means that these arguments are really useful for system administration tasks. That's because we can specify the information that we want our program to use before it even starts. This lets us create more and more automation. And you can't argue with that, although you could argue my humor isn't really that humorous. But what can I say? I'm a better coder than I am a comedian. Anyway, we can access these values using the argv list in the sys module. Let's check this out by executing a very simple script that just prints this value. First, let's use our friendly cat command to look at what the script does. As you can see, our script just imports the sys module and prints the sys.argv list. Now, let's see what happens when we call the program. In this case, we called the script without any parameters. The list contains one single element, the name of the program that we just executed. Let's try passing a few parameters. Now, we see that each of the parameters that we pass is included as a separate element in the list. And last up, we have the concept of exit status, or return code, which provides another source of information between the shell and the programs that get executed inside of it. The exit status is a value returned by a program to the shell. In all Unix-like operating systems, the exit status of a process is 0 when the process succeeds, and different than 0 if it fails. The actual number returned gives additional info on what kind of error the program encountered. Knowing if a command finished successfully or not is helpful information, which can be used by a program that's calling a command. For example, it can use the information to retry the command if it failed. To check the exit status of a program, we can use a special variable that lets us see what the exit status of the last executed command was. The variable is the question mark variable, so to see the contents, we use $?. Let's try this out using the wc command, which counts the number of lines, words, and characters in a file. First, we'll pass it our variables.py script and check the exit value. So here, we first ran the wc command and it printed the values of lines, words, and characters for our Python script. Then, we printed the contents of the $? variable and we can see that the exit value was 0. That's because wc ran successfully. Here, wc couldn't run for the file that we passed because it doesn't exist. The command printed an error, and when printing the contents of the $? variable, we see that it finished with an exit value of 1. So, that's for system commands. But what about Python scripts? When a Python script finishes successfully, it exits with an exit value of 0. When it finishes with an error, like type error or value error, it exits with a different value than 0. We can make it exit with whatever value is relevant. Let's check out an example of this. This script receives a file name as a command line argument. It first checks whether the file name exists or not. When the file doesn't exist, it creates it by writing a line to it. When the file exists, our script prints an error message and exits with an exit value of 1. To try this out, let's first execute the script and pass a file that doesn't exist. Nice. Looks like that was successful. Check out how it exited with the exit code 0, even though we didn't specify this in the code. That's because that's the default behavior. Let's look at the contents of the file to make sure it's got what it should. Okay, and what do you think will happen if we now run the command again? You guessed it, we get an error because the file already exists. And so we get an exit code of 1. So we've now seen how we can pass command line arguments to our Python programs and how we can make our programs tell us whether they've finished successfully or not. These are both important tools that we'll use when creating automation. We'll use command line parameters to tell our programs what we want them to do without having to interact with them. And we'll use exit values to know if our command succeeded or failed, and then log failures and automatically retry the commands if we need to. Whoa, we've definitely learned a lot over these last few videos. Chances are it got a little tricky at some points, but you're doing an awesome job not letting these complex concepts stop you. Up to now, we've been using Python to interact with the operating system through baked-in functionality. For example, we've used file objects to read the contents of files, use the shutil module to check if the disk is full, and use a sys module to process standard input, get parameters, or generate an exit code. But what if we needed to run a system program from a Python script? Say, for example, that as part of a Python script, we needed to send ICMP packets to a host to check if it's responding. We could try to look for an external module that provides this functionality. Or we can just run the ping command, which will send packets for us. Sometimes it's easier or faster to use a system command as part of our Python script to accomplish a task, or use some functionality that doesn't exist in the Python modules, neither built-in or external. For these cases, Python provides a way to execute system commands in our scripts using functions provided by the subprocess module. Let's check out an example. First, we'll import the subprocess module, and then we'll call the date command, which shows the current date using the subprocess.run function. The run function returns an object of the completed process type. This object includes information related to the execution of the command. From the information that got printed, we can see that the return code of the command was 0. To run the external command, a secondary environment is created for the child process or subprocess where the command is executed. While the parent process, which is our script, is waiting on the subprocess to finish, it's blocked, which means that the parent can't do any work until the child finishes. And I bet a lot of parents out there are saying, I know that's right. After the external command completes its work, the child process exits and the flow of control returns to the parent. Then the script can continue its normal execution. Let's see this in action by calling the sleep command, which waits for a number of seconds that we tell it before returning. You may have noticed that while the sleep command was running, the interpreter was blocked and we couldn't interact with it. That's exactly what we mean about the parent process being blocked until the child process is done. Check out how we called the command. The run function receives a list that starts with the name of the command that we want to call, followed by any other parameters that we want to pass to that command. So, any elements following the program name are the command line arguments for it. In this case, we're requesting sleep to wait for 2 seconds. In the last two examples, the commands executed successfully, and so the return code inside the completed process instance was 0. Let's check out an example where the exit status isn't 0. If we call ls with a file name that doesn't exist, ls will print an error and return an exit status different than 0. This will be stored in the return code attribute of the completed process instance, and we can access that value in our code. We can see that the command failed and the return code stored was 2, letting us know that there was an error. We could use this information in the script to do something different in case of failure. Using the run function like this is useful if we just want to run a command and only care about whether or not it was successful. The output of the command will be printed to the screen, which means that our script has no control over it. This can be handy for system commands that either don't have useful output, like cp, chmod, sleep, and many others, or when we don't care about processing that output any further. In other words, when it's just fine to have the output printed to the screen. For example, if we're writing a script that's changing the permissions of a bunch of files in a tree of directories, we don't care about the output of the chmod command. We only want to know if it was successful or not. If instead we want to capture the output of an external command and then operate with the results, we need a different strategy. We'll dive into that in the next video. I'll see you there. If we want our Python script to manipulate the output of system command that we're executing, we need to tell the run function to capture it for us. This might be helpful when we need to extract information from a command and then use it for something else in our script. For example, say you wanted to create some stats on which users are logged into a server throughout the day. You could do this with a script that calls the who command, which prints the users currently logged into a computer. The script could parse the output of the command, storing the list of logged in users once per hour and at the end of the day to generate a daily report. To be able to process the output of commands, we'll set a parameter called captureOutput to true when calling the run function. For our next example, we'll call the host command, which can convert a host name to an IP address and vice versa. When calling it, we'll pass the captureOutput equals true parameter and store the result in a variable so that we can access it. Let's give it a try. We know that the result variable is a completed process instance that we can access. We can check the return code attribute like we did before. And we can also print and operate with the output generated by the command, which is stored in the stdout attribute. What's that B at the beginning of the string? Well, that B tells us that this string is not a proper string for Python. It's actually an array of bytes. An array of bytes? This is a complex subject, so listen closely. Data in computers is stored and transmitted in bytes, and each can represent up to 256 characters. But there are thousands of possible characters out there, used to write in various languages. Chinese, for example, requires over 10,000 different characters. To be able to write in those languages, several specifications called encodings have been created over time to indicate which sequences of bytes represent which characters. Nowadays, most people use UTF-8 encoding, which is part of the Unicode standard that lists all the possible characters that can be represented. So, going back to our example, when we execute the command using run, Python doesn't know which encoding to use to process the output of the command. So, it simply represents it as a series of bytes. If we want this to become a proper string, we can call the decode method. This method applies an encoding to transform the bytes into a string. By default, it uses a UTF-8 encoding, which is what we want. So, with all that said, let's transform our array of bytes into a string and then split it into several pieces. In this way, we're operating with the output of the command that we ran, and we can do whatever we need to do with it. For example, we can choose to keep the last element of the list, which is the name that corresponds to the IP that we're looking for. Great, so we just looked at the captured standard output, but what about standard error? If we use the capture output parameter and the command writes any output to standard error, it'll be stored in the stderr attribute of the completed process instance. Let's look at an example of this. We'll try executing the rm command, which we use for removing files, passing a file name that doesn't exist. Let's check the return code of the command. Okay, it failed, just like we expected. Now, let's check the contents of the stdout and stderr attributes. So, we see that, in this case, the standard output was empty, but there was an error printed to standard error which we can access through the stderr attribute. This is a great example of how standard output and standard error are actually different streams, and so Python captures them separately. Okay, we've now seen that we can execute system commands from Python and check whether they succeeded or failed. We've also seen how to capture their standard output and standard error streams so we can use their content in our scripts. These skills can be super useful when writing scripts that use system commands for some involved tasks and letting our Python scripts cover a broader range of tasks. Alright, so we've seen how to run system commands from Python, how to check the exit value, and how to manipulate the normal output and error output of a command. The subprocess module offers a lot of extra options that we can use in our scripts. For example, we called out in an earlier video that one way of providing information to our processes is to modify the environment variables. Using this mechanism, we can change where the process looks for executable files, which commands it uses to interact with some parts of the system, the kind of output it'll generate, and a bunch more things. The usual strategy for modifying the environment of a child process is to first copy the environment seen by our process, do any necessary changes, and then pass that as the environment that the child process will see. Let's take a look at this. So, in this code, we start by calling the copy method of the OS environ dictionary that contains the current environment variables. This creates a new dictionary that we can change as needed without modifying the original environment. The change that we're doing in this script is adding one extra directory to the path variable. Remember, the path variable indicates where the operating system will look for the executable programs. By adding one entry to the path, we're telling the OS to look for programs in an additional location. To create the new value, we're calling the join method on the OS path sep string. This joins the elements of the list that we're passing with a path separator corresponding to the current operating system. So here, we're joining /opt/myapp and the old value of the path variable to the path separator. Finally, we call the myapp command, setting the end parameter to the new environment that we've just prepared. So, to recap, this script is modifying the contents of the path environment variable by adding a directory to it. We then call the myapp command with that modified variable. Doing it this way, the command will run in the modified environment with the updated value of path. There are a bunch more options that we can use with the run function. For example, we can use the cwd parameter to change the current working directory where the command will be executed. This can be really helpful when working with a set of directories where you need to run a command on each of them. We could also set the timeout parameter. This would cause the run function to kill the process if it takes longer than a given number of seconds to finish. This might be useful if you're running a command that you know might get stuck. For example, if it's trying to connect to a network and your computer is offline. Or we can also set the shell parameter. If we set this to true, Python will first execute an instance of the default system shell and then run the given command inside of it. This means our command line could include variable expansions and other shell operations. Without the shell parameter, this would not be possible. We'll learn more about the things that we can do with the shell later in this course. For now, just keep in mind that if you need to expand variables or globs, you'll need to set this parameter. But using this can be a security risk, so make sure you actually need it and be careful when using it if you do. Before we finish our discussion of the subprocess module, a word of caution. Interfacing with the underlying system directly in your Python scripts via subprocesses and system commands can be useful, especially if you need to do a specific task quickly, but it comes with some drawbacks. Using these system-level commands builds assumptions into our scripts about the infrastructure our automation will run on. And if those assumptions change, it can lead to unexpected effects or failures. These kinds of assumptions can change in multiple ways. What would happen to our automation if the flags for a terminal command change and our script continues to use the old flags? What happens if we switch operating systems from Linux to Windows? Will our scripts fail outright, or will they succeed in unintended and possibly harmful ways? Any change to the system or external commands our scripts use increases the chances of something breaking. Sometimes that break might be obvious, and other times it might be difficult to detect. If we're automating a one-off, well-defined task where developing a solution quickly is the biggest requirement, then using system commands and subprocesses can help a lot. But if we're doing something more complex or long-running, it's usually a good idea to use the baked-in or external modules that Python provides. So, before deciding to use the subprocesses, it's a good idea to check the standard library or PyPy repository to see if we can do the task with native Python, and to check if someone has already created the automation that we wanted to write. Remember that we never want to reinvent the wheel. How's this all sounding? That was a lot of info about advanced subprocesses, and it may take a little time for it to all, well, sink in. Now it's a good time to use your local Python installation and try out some functions and commands that we saw. Whoa, you're on a roll working through these new techniques. So far, we've learned a bunch of new concepts that let us interact with the system. We've learned how to read and write files, how to use regular expressions to process them, how to interact with the system shell, and how to execute commands in that environment. That's really impressive, so take a quick moment to think about how far you've come and about all the new cool stuff you'll be able to do by interacting with the system. Now, we're going to take a look at how we can use these tools to help us with our day-to-day work. In the next few videos, we'll dive into a concrete example centered around processing chunks of data, the kind of data you might find in a syslog file or a web request log. The different events that happen in programs that are running in a system and aren't connected to a terminal are usually written to log files. Log files contain a lot of useful information, particularly when you're trying to debug a tricky problem that's happening on a computer. On the flip side, sometimes it can be overwhelming to try to find something inside of a log file that contains a whole lot of lines with a whole lot of things in them. So it's a good idea to learn how we can process these files and get our tools to extract information that we want out of them. To do this, we'll go back to our knowledge of regular expressions. Using regexes in our scripts gives us a great deal of flexibility when processing log files and other text data sources too. In a script, we can program any kind of behavior we want, so we can manipulate and process text data and get results we need. We're going to show you how you can do this in the next couple of videos. All right, let's get started. When working with log files in a script, our first step is usually to open them so our code can access their contents. We've discussed various methods of operating on files. The usual technique is to call the open function, which returns a file object, and then iterate through each of its lines using a for loop. For example, to open a file received as a parameter of our script, we can use code like this one. Remember that, for performance reasons, when files are large, it's generally a good practice to read them line by line instead of loading their entire contents into memory. For our example, let's say the log file contains these messages. The server that generates this log file has been acting strangely, and we suspect it's due to a cron job started by one of the system administrators. You might remember that cron jobs are used to schedule scripts on Unix-based operating systems. To find out what's happening with the server, we want to audit the log files and see exactly who's been launching cron jobs. By looking at the sample log, we can see that the lines that will be most interesting to us are the ones that contain the cron substring. These lines also show the user who started the cron job wrapped in parentheses. With this info, we can ignore any line without the cron substring in it. We can check for this using the in keyword. Here, we're using the continue keyword, which tells our loop to go to the next element. So, if the line doesn't contain the string that we're looking for, we'll skip it and go to the next line. Once we know we're processing the right log line, we can use our knowledge of regular expressions to extract the username. We can do this in a bunch of different ways. In this example, we'll use escape characters, capture groups, and the end of string anchor. Before we add the expression to our script, we'll construct it and test it out in an interpreter. Let's take a closer look at this expression. Since the username is found at the end of the log line, we use the $ anchor to only match text that is at the end of the line. To find the username, we look for the word user followed by a string wrapped in parentheses, as that's how these lines are structured. This means that we need to escape those parentheses with a backslash. And since we want to extract the actual username, we use another couple of parentheses to create a capturing group. And for the username itself, we're matching any alphanumeric characters by using \W+. With that cleared out, let's test it out with a sample line. Tisk tisk, looks like we've got a naughty user. On the plus side, it seems that our regular expression works correctly. We can now use the expression in our code. Let's add it to our script. Okay, our script should be able to process the log file that we showed earlier. Let's save it, make it executable, and run it, passing the example syslog file that we showed. Our script is shaping up nicely. We've located each user that started a cron job in our log file and printed them to the screen. Pretty nice, right? We took a few steps to craft this script. If any of these steps were unclear, review the video and practice on your own until you get it. Up next, we'll do a bit more processing with those results. In the last video, we wrote a script that processed a log file and extracted the names of each user who had started a cron job in the machine that we were investigating. This can be really helpful, but there's more information that we might need. To improve our output, it would be a good idea to have a count of how many times each username appears in our log. Can you think of what we can use to do that? If you guess a dictionary, then you're right. As we've seen in earlier examples, dictionaries are a great structure to use when we want to count appearances of strings. We'll store the username as the keys of a dictionary, and we'll use the value to count the number of times that each username appears in the file. To do this in fewer lines, we'll use the get method that we saw earlier in another video. Let's try it out in the interpreter before adding it to our code. First, we'll create an empty dictionary using curly brackets. Then, we'll set the variable name as good user, for example. And now, we'll set the value associated with the key as one more than the current value, and we'll use the get method to get the current value, like this. Again, we're taking the current value in the dictionary, but passing a default value of 0, so that when the key isn't present in the dictionary, we get a default value. We then add 1 and set it as a new value associated with that key. Let's check out the current contents of the dictionary. Great. And what happens if we do the same operation again? Fantastic. We see that this operation works successfully both when the key is already in the dictionary and when it isn't. Now, let's add this to our script. We'll need to initialize the empty dictionary at the beginning of our code. And before we add any values to the dictionary, we want to check that we actually got a match to our regular expression. Do you remember how we can do that? We can check if the result variable is none. We'll use that same technique as before, and use the continue keyword if the result is none. Okay, we can now add the values to the dictionary as we process the file instead of printing them. To do that, we'll define a name variable that will store the captured group. And then we'll use that one as a key for our dictionary. And finally, let's print the resulting dictionary once we're done going through the file. Nice. Our modified script is ready. Let's try it out with our test file. Cool. Our script now allows us to very quickly see who's been starting cron jobs on the server and at what frequency. Now, we can use the information to investigate the issue more deeply. It's pretty cool to see how all these different ways of managing data and processes come together in a real-world example, isn't it? Nice job. Hopefully, these examples are helping you see how your Python programming skills can help you quickly get the information that you want when you're debugging a problem.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.